Welcome back. Our next speaker is Christine Spang. Let's give her a warm welcome.
Hey everybody, good afternoon. Hey. We're going to be talking about WebSockets today. So WebSockets are cool because they enable us to build web applications that are both real-time and that scale really well. So in this talk, I'm going to give you some historical context for why we needed WebSockets in the first place. Then I'm going to explain to you how the protocol actually works at the protocol level, and we'll take a look at a TCP dump of WebSockets in action. I'll also talk about things that you need to keep in mind when running WebSockets applications in production. All right, a little bit about me. My name is Christine Spang. I've been programming since I was in high school. After that, I went to MIT, and then I spent 3 years working at a company called Ksplice. So Ksplice developed a technology for the Linux kernel that allows you to update the running kernel without restarting it, which is pretty cool. Today, I'm one of the co-founders at a company called Nihilus, a startup in San Francisco. We're building a platform that makes it easy for you to build applications that use data from email, contacts, and calendars. All right, enough with the intros. Let's get to the talk. First, we're going to talk about what WebSockets are. Then I'll give you a Python example, and an example that's a bit more real-world than the basic example. Then we'll talk about performance and their use in production. All right, let's dive in. So, what are WebSockets? To answer this question, I'm first going to give you some of the history of protocols powering web applications, the shortcomings they had, and how web developers attempted to address those shortcomings. Along the way, I'll show you how WebSockets took a concept that's been around as long as servers have been around and adapted it for the web to enable new kinds of web applications to be built. So here's a diagram that shows how HTTP works. How many of you here have used HTTP, understand how it works? OK, good. That's good background for this talk. So to quickly review, you have web servers, which host the static HTML pages and the code that makes up a web application. And then you have browsers, which are clients which talk to the web server using HTTP to retrieve content to show users via their browser. Here's an example of what a typical GET request in HTTP looks like. You can see that the basic request is the verb get and the argument, in this case slash. And then we have a whole bunch of other information in this request that are headers that go along with the request. And you can see from just the excerpt up here in this super basic request that most of an HTTP request is actually the headers and not the actual action that we're trying to do. This is important for later. So to continue with the background, the web was originally created by Tim Berners-Lee to share static academic documents. And so this basic model, where a client requests a page, opens a connection to do that, and gets a page back, worked really well to share academic documents. But as time went on, people wanted to create actual software programs where most of the work was done on the server, and the browser just acts as a thin client, retrieving new data and rendering it to the user. So there are a number of reasons to want to do this, such as not having to distribute new updates to the application to users' computers. With a simple HTTP model, you can create interactive applications. The main wrench is that every time some interaction happens, say a user clicks on a link or a button, or the app wants to refresh the page to update the information being displayed, it has to initiate an entirely new HTTP connection to the server, send it the request, and receive a response. And as I showed on the previous slide, it turns out that there's a lot of data being sent in every HTTP request. The average HTTP header request is actually about 800 bytes. So this slide previously shows a really basic request, but more complex requests, which are very typical, very common, contain even more headers, such as cookies, which are actually sent on every single HTTP request. So when we create web apps using plain old HTTP, but once you start to trying to do things that are much more interactive, you start running into the problem that this model is very slow. We could refresh the page every time we wanted to let users interact with the site, but it takes a long time to send requests back and forth to the server as well. Even in the best case scenario, we're limited by the speed of light. So between Boston and San Francisco, in the best case, light takes about 40 milliseconds to go back and forth. And in a more average case, you're looking at like 80 milliseconds latency of coast to coast. So plus more time to transfer any data, which includes those HTTP headers, which, as I previously stated, are really big, and also time to bootstrap the TCP connection. So if you're going to transfer a lot of data using TCP, you have to bootstrap the connection over a couple back and forths to increase the window size. So developers tried to work around these problems in a number of different ways. One of the first ways was this method that ended up being called AJAX, which is short for asynchronous JavaScript. Basically, you have a piece of JavaScript in your web app, and you wire that piece of JavaScript up to a button that you want to talk to the server, and the JavaScript can asynchronously send a request to the server, get the response, and then potentially update a subset of the current page with new data. So this allows us to update pages without completely refreshing them, but it still has to create another HTTP connection, including opening a new TCP connection, to the server every time it wants to send data back and forth. Clients can use AJAX to poll a web server for updates to a page as well, basically making a new connection at some interval to ask for updates. So this was an improvement on the simple model where you just send a GET request and get the response back, reloading the whole page. But it didn't fundamentally change the model of how web applications operated. One problem was that if computation was happening on the server and the client wanted to keep updated about the server's current state, it had to poll or keep checking in with the server at some interval and create a new connection every time. So another limitation that web apps had compared to, say, a desktop application was that up until this point in time, the communication between the client and server was fundamentally one way. So web developers are really smart people, and they came up with a way to work around this as well. The thing they came up with next was a model called Comet, or sometimes long polling. This involves keeping a long-lived HTTP connection open until a timeout expires or the server has some data to return to the client. The client then opens another HTTP connection to the server and continues to wait for data. So this worked pretty well, actually, but there was one case that was left where it still degraded, and that's if the application needed to pass data or messages back and forth from the client to the server at a really high interval. So this is an actual quote from one of the WebSockets RFCs. And it says, historically, creating web applications that needed bidirectional communication between a client and server, e.g. for instant messaging and gaming applications, has required an abuse of HTTP to pull the server for updates while sending upstream notifications as distinct HTTP calls. So it's right there in the RFC why we needed to come up with something that was different. Oh, whoops. That's not right. In order to be able to implement proper real-time applications, apps that were sending small messages back and forth between client and server often, we really needed a protocol that allowed two-way communication between client and server with low latency. And that's where WebSockets came in. So now you have some historical context. Let's talk about how the WebSocket protocol actually works now, so we can better understand how it evolved and how it allows different kinds of apps to exist on the web. In order to do this, we have to take a look at another piece of computing history, or what the word socket actually means in a computing context anyway. In the 1970s, when Unix was developed at Bell Labs, part of the operating system API that Brian Kernighan, Dennis Ritchie, Ken Thompson, etc. created contained an API they called a socket. I have no idea why they called it this, and I asked the internet why they called it this, and no one knew either, so who knows. So Unix domain sockets were used for local interprocess communication, or IPC, on a single server. You would make a call to the socket syscall with the AF_Unix domain, and then you'd get a file descriptor you could use to communicate between processes. The socket was a bidirectional link between two different programs, which it could use to send messages back and forth. If you use the socket syscall in Linux, you can also use it to create a socket that goes across the network. So your program on a local computer can open up a socket to a game server, for example, and the game server can send the program updates, or vice versa. So the Linux socket API is really super simple. It consists of three syscalls: socket, which creates the socket descriptor, and then there's send and receive, which are used to pass messages back and forth. I bring all this up because it turns out that you can think of WebSockets as basically Unix sockets for web applications. The WebSockets protocol and API were introduced as a part of the HTML5 specification, but they were eventually split out to their own RC in order to keep HTML5 simpler. Before WebSockets, there were some ways to open up socket connections in web applications, but there was no standard API for it. You had to use a non-standard browser extension like Flash in order to do it. The WebSocket spec made the idea of using sockets for web applications standard, and also dealt with problems unique to web applications trying to use sockets, like dealing with firewalls and proxies. So the things laid out in the WebSockets RFC with how the WebSockets API works and the protocol works were specifically designed to make it easy to use sockets using existing web infrastructure. So, for example, it's a problem to use sockets on different ports than port 80 or port 443, because proxies and firewalls will actually drop traffic or block traffic to these ports. So WebSockets were specifically designed to be backwards compatible with this infrastructure. So WebSockets make real-time apps possible on the web. But what's a real-time app? Basically, that means anything updating, live updating, at high frequency. For example, games, stock tickers, chat programs. The chat program Slack, for example, uses WebSockets to connect from the web browser client to the server. So now I want to take a look at a super simple WebSockets example using Python. All right. Here we go. Not this one. We want this one. OK. Hopefully you guys can see that OK. So I've created a little example here using the WebSockets library, which is a Python 3 only library that is built using async.io. So let's take a really quick look at this code. you can see that it consists of a single function and basically uses this WebSockets library to serve that single function on localhost on this port 8765. And then it just runs in a loop forever and serves this function to every connection that connects to this port. Sure. I think I'm gonna like do it here, or like make a new terminal. It's really annoying to bring things up in Vim because the color scheme is terrible on a projector, so hold on one moment. Okay, I don't want to like spend too much time fiddling around with this, sorry. I can do like this. Oh, whoops. Make it bigger. Success! You don't get syntax highlighting now, though. But there's not a lot of code here, so you don't really need the highlighting. Basically, this uses the yield from expression from Python 3 to make this asynchronous. And, oh, this is the client, right? So the client, I was looking at the server before, but the client will connect to the server right here. So WebSockets URLs look like WebSocket : // Then you'll do WebSocket.send to send a message. And then in the server, you can actually see that it does WebSocket. Whoops, that's not right. All right, WebSocket.receive to receive a message, and then I can also use WebSocket.send. So this is exactly the same API as we saw on the Linux socket API. It's create a WebSocket, send, and receive. Super simple. And I actually want to show you guys this running. So we can fire up a server. Oh, whoops. Virtual env. Okay, so now the server's running. And then I want to make this bigger. So then we can fire up the client and say, hi, my name is Spang. And it says hello. And then we can go back to the server and see it also says hello. So if this were a better demo, I would do lots of these in parallel, and you could see that it would just send this at the same time. But this is a super simple example. And I want to keep it super simple because I actually want us to take a look at what actual traffic is going over the wire. So you can use a program called TCP dump to capture internet traffic between two different servers or between the same server, between your laptop and your laptop. And I want us to do that right now. So I'm not going to run like the super live TCP capture, but I'm going to show you how to do it, just in the sake of time. So generally, to capture WebSockets traffic, you'd run TCP dump, and it has a lot of obscure arguments that you should read the man page to find out what they actually mean. But basically, to capture WebSockets traffic, you want to capture TCP traffic and HTTP traffic on this specific port. And this says to like output it to this dump file. So I actually have this dump file, WebSocketSimple.dump, which is a TCP dump capture file. And then there's this handy-dandy tool for looking at web traffic that is called Wireshark that we can use to take a look at this. So if I pull up this dump file in Wireshark, so I want to clear the filter here first. So this is a dump of doing the same interaction that we saw before, and that was like connecting a simple client and seeing the server respond to it. So you can see that it bootstraps a TCP connection. Sin, ack. All right, we got a TCP connection. And then it sends an HTTP request. So this is a really important part of WebSockets. And it has to do with this whole backwards compatibility thing that I said earlier. In that a WebSockets connection is bootstrapped over HTTP. So when you have a WebSockets application, you send an HTTP request to start it, because everything understands what HTTP is, and not everything understands what WebSockets are. So yeah, here we go. So I want to apply a filter on this so we get rid of all the TCP bootstrapping packets. Yeah. Oh, whoops. HTTP or WebSocket. There we go. OK, cool. So this is the interesting stuff here. So you see it starts with a get / bootstrapping over HTTP. Then you can see the next part is a special HTTP status code called 101 switching protocols. So 101 switching protocols is how the server tells the client that we're going to switch over to using WebSockets instead of basic HTTP. So after that, we dive into the WebSockets frames. So WebSockets were designed to be super minimal in that the overhead per frame is really small. So you can actually use Wireshark to take a look at the actual data that's being sent. And if we see here, it's WebSocket, and it will show you the actual data that's in this packet. So the first things up at the top are the padding. This is one bit called fin, which designates whether or not this is like the last packet. So if you're sending a bunch of data, you're going to have multiple frames. So this happens to be a small packet, so it says 1, yes, it's the end. Then there's a few reserved bytes. Then there's an opcode, so you can send WebSockets data in text or binary. Then there's this thing called a mask. And the mask is also part of why WebSockets are compatible with existing internet infrastructure. So the mask and the masking key are used by clients sending data to the server to obfuscate the payload, which makes it less likely that various servers in the middle, like between various different packet hops, will mess with the payload and just break everything. So then we also have a payload length, so we know how many packets to expect. And then we actually just have the packet, or the payload. And you can see, I don't know if this is decoded. Oh yeah, so you have the payload here, and then you have the payload with the mask applied. So you can see it was just sending my name, Spang. So that's the basics of how the protocol works. So it's super simple. And let's go back to the slides. Here's a little diagram of this WebSocket protocol bootstrapping process that we talked about. So again, you start the process using basic HTTP. You issue a GET request. Then the server will respond with connection upgrade. Then the server also responds with this special code called HTTP 101, switching protocols. And then the conversation can continue from there, sending messages back and forth. Either the client or the server can send a message either way at that point, because we're using WebSockets and not HTTP. And that connection will be closed as soon as either the server or the client closes it, because it's bidirectional. We already talked about this. Switching protocols, that's how it starts up. OK, so now I want to show you guys an example that's a bit more real world. Back in the day when, I think it was like 2006 or 2007 or something like that, when WebSockets were super new, Mozilla created this game called Browser Quest in order to demonstrate how WebSockets were interesting and useful. So games are a really great application for WebSockets because if your character's moving around, you might want to send like little updates about where the character's moving to, or like if there's like a battle going on, you want to like send those battle commands and like update all the other characters that are logged into the same server. And it's important to be able to scale these things to large sizes, so the amount of data that you're sending over the wire can be really important. So the browser request game was a little bit bit-rotted, so I had to fork it to make this work. But I did, but they told me that they're not maintaining it anymore, and they wouldn't take it. So you'll have to use my fork if you want it to work. I'm sure that will be a more compelling case. All right, cool. So I have a VM that I set up that's running this game. Unfortunately, the game is also written in Node.js. Blame Mozilla. So here's the game server running in my VM. And then I'm going to close these ones that I'm not using anymore. I don't need that one. I don't need Wireshark anymore either. Make it go away. Okay, so this is the game, and then actually we need a web browser, which is our client. So I think I have it running on this local IP address here. Oh no, damn it. Okay, I want it to start from the beginning. And I also want to use the Chrome DevTools. All right, Chrome DevTools are awesome, by the way. Okay, so we connect, and then it asks for your name, so I'm going to say Spang. And then we can say play. So that was it. It was connecting to the WebSockets server. And usually when you're running a WebSockets application, you run it behind a proxy that, like Nginx or Apache or whatever. Okay. So then what I want to look is the network tab here. And the interesting part of the Chrome DevTools, so Chrome DevTools have native support for debugging WebSockets. And all you have to do is scroll through this really long list of resources loading and find the one that's WebSockets. So give me 1 second. Where is the filter, by the way? On the left? Which button? Oh, the search? The funnel. Okay, thank you. 101. No. Oh, here we go. Nice. Awesome. Thanks for that tip, guys. Okay, so then over here on the right, you have the general information about the WebSockets connection. And then you can look at the individual frames. So, oh, here we go. There you go. So you can see that whenever I click somewhere, it is sending some data back to the server. And then if we go back to our terminal, you can also see that it's like Spang is moving to 39,209, received 26.2. So it's sending these lists of numbers back and forth. So we're running out of time, so I'm going to try to wrap this up. But the really interesting thing here is that this could scale to a ton of connections because we're only sending tiny little bits of data. Okay. All right, I got to wrap this up. So I'm going to go through like 2 slides more. So performance, just to remind you, WebSockets have overhead of like 2 to 14 bytes compared to HTTP, which is like 800 bytes per connection. You probably only need to use WebSockets if you need to scale your application to a lot of connections, because otherwise it doesn't really matter. So about 80% of browsers today have support for WebSockets, and 20% don't. So you should use a polyfill library, usually Socket.io, in order to not make your application not work for those apps. Okay. All right. So that's all I have for you folks today. This went a little bit quickly, so I also have some links here if you want to learn more. And I didn't really get a chance to go into specifics about what you should use with Python. There's a library called FlaskSocket.io, which I think is a good choice for building apps that need a polyfill. Thank you. What's that? Yeah. If you have questions, I'll be outside because we don't have any more time right now.